In an earlier video, we have talked about the work done by certain kinds of forces. So for example, work done due to gravity was defined as minus mg delta y, where delta y is defined as y final minus y initial. So this was a case where, let's say we have a particle P that's being moved from position P1 to position P2, and with respect to some reference line which we call datum. So this is a reference line, let me call it reference line, and this is a horizontal line. We are given vertical distances for initial and final position of the particle. So initial position is at a distance y1 from datum, and final position is at a distance y2 from datum. And the force of gravity acting on the particle is in the downward direction. So at any intermediate configuration, if you draw a free body diagram, you can look at the forces that are acting on it. And in this case, we're assuming the only force is the force of gravity. So in this case, we opt in the work done as minus mg y2 minus y1. So for example, if you go from a lower elevation to a higher elevation, then the work done clearly would be negative. So let's say, do an example. Let's say initial y1 is 5 meter and final y2 is 10 meter, and the weight of the particle is given as, let's call it, I don't know, 10 Newton. Then the work done would be equal to minus mg, which is 10, times y2 minus y1, so that's 10 minus 5, so that will be minus 50 joules. So the work done is negative, as you can see in this case, because you're going from a lower elevation to a higher elevation. So in this case, we are saying that we have to do work against the gravity to go to a higher elevation, and that's why the work done is negative. On the other hand, if you were traveling in the reverse direction, so if you were, instead of going this way, so let's say one path is this path, so this is the path, and you're going in this direction, clearly the elevation is increasing, you could go in the opposite direction. So you could come down, actually, let's say from y2 to y1, come down that way, and in this case the work done would be equal to, we still have minus 10 mg, but now y2 is going to be essentially y1, because that's the final position, and this will be y1, so that would be 5 minus 10, right? Because y2 in this case is y1 and y1 is y2, so that would be equal to minus 10 times minus 5, so that will be plus 50 joules. So that's the work done by the gravity. So in this case, we say that the gravity is assisting the system in bringing it down from a higher elevation to a lower elevation. So positive sign and negative sign of the work done tells you something about whether the work is being done against the system or is being done by the system. Now let's come back to our original formula for the work done due to gravity, which is defined as minus mg y2 minus y1. Now, when you look at this formula, there's one thing you notice is that this expression is actually independent of the actual path taken, okay? It only depends on what the final elevation is, what the initial elevation is. So we will define a potential energy function due to gravity called U sub g as mg times y, okay? So if we define it that way, then ug in position 1 would be written as mg times y1, and ug in position 2 would be written as mg times y2. Okay, now if you had another third position, you could write that as well, something like, let's say, ug3 equal to mg times y3. So if we define this as a function, then w sub g can be written as minus mg y2 minus mg y1. That's our definition for the work done, and that would be minus ug in position 2 minus ug in position 1. Or in other words, we can write it as minus delta u sub g. Sub g over here indicates that this is the work done due to gravity. So we would get that. Now, this function over here is defined as potential energy function due to gravity. So this kind of tells you that potential energy functions could vary from force to force. So this is the potential energy function for gravity. Perhaps you will have another kind of potential energy function for another kind of force, and we'll look at another example of this. Okay, so that's how we define the work done due to change in potential energy. So we say that when we actually do the work against the system, we are building potential energy into the system. So when you go from a lower elevation to a higher elevation, you're essentially putting potential energy into the system that can be used when you need it. Now let's look at work done due to elastic forces. So work done due to elastic forces were defined as minus 1/2 kx2 squared minus 1/2 kx1 squared, where, let me draw this again. So we have a spring, we have a block attached to it, that's K, and this is the mass M. X1 would be the initial stretch. So let's say this is the no stretch configuration. And then we stretch it by a certain amount from the no stretch position to, let's say, X1. And its final position is X2, again from no stretch position. So the block has been stretched from position X1 to position X2. So X1 is the actual stretch and X2 is the actual stretch in the final configuration. Those are not the lengths of the spring. Keep that in mind. So let me write that. X1 and X2 are stretch or compressions. So they don't have to be stretch only. They could be stretch or compressions. They are not the length of the spring. So in this case, if we want to express the work done due to elastic forces, so first of all, I made a slight mistake. This is actually not W sub G. This should be W sub E because we're talking about elastic forces. Okay. So W sub E can be written as minus 1/2 kx2 squared minus 1/2 kx1 squared. Let me write that again once, basically here. And I'll call potential energy function U sub E to be 1/2 kx squared. Okay, so UE in position 2 would be 1/2 kx2 squared, and U sub E in position 1 would be 1/2 kx1 squared. Okay, so in this case, WE would be minus UE2 minus UE1, which is nothing but minus delta U due to elastic forces. So once again, the work done due to elastic forces is expressed as a difference in potential energy function. So potential energy function over here is 1/2 kx squared. So this is the potential energy function. Sometimes people will also say it's simply potential energy due to linear elastic forces. So what we are trying to say over here is that when the work is done by the force or against the force, and the force is a special kind, and we'll define what that special kind of force is, then the work done by that force can be expressed as change in potential energy. So potential energy over here basically tells you something about the energy that would be stored in the system due to this special configuration. So for example, the mass is moved from distance y1 to distance y2, or the mass over here in the spring mass system is stretched from one position to another position. So due to its configuration, it has potential energy associated with that. Okay, so that's good. But we also know that the work done is defined as change in kinetic energy, right? So change in kinetic energy. And we have just seen that the work done can also be written as minus delta U. Now, delta U over here is basically the delta of potential energy due to all kinds of forces for which the work done can be represented as change in potential energy. So let me write this again. So let's say the forces acting were both gravity as well as elastic forces, then this would be delta U due to gravity plus delta U due to elastic forces. Now, if you had other kinds of forces for which the work done could be expressed as a change in potential energy, then you could add those changes as well. Now, one of the forces for which you cannot write the work done as change in potential energy is friction. Okay, friction is not the kind of force for which you can write something like this. So W equal to minus delta U may not necessarily be written for friction forces, because friction forces do not have a corresponding potential energy function. So once we have this, we can write delta T equal to minus delta U, because W is delta T and is also equal to minus delta U. So this would be delta T plus delta U equal to 0, which can be written as delta of t plus u equal to 0. Okay, and this is basically saying that the change, so delta is the change in t plus u. Now t plus u, what is that? T plus u is nothing but kinetic energy plus potential energy, right? And these two together are called mechanical energy. Mechanical energy. So this will be right as ME. Okay, change in kinetic energy plus potential energy is actually equal to 0. And what does that tell you? It tells you that the kinetic energy and potential energy combined together are constant as the system or the particle moves from one configuration to another configuration. So this can be written as T1 plus U1. So this would be the total mechanical energy in configuration 1 equal to T2 plus U2. That would be mechanical energy in configuration 2. And this is called conservation of mechanical energy principle. So what this is saying is that you can conserve the total mechanical energy of the system if the forces that are acting on the system are such that the work done by them can be expressed as change in potential energy. And I've already told you that at least there is one kind of force, which is friction force, for which you cannot write the work done as change in potential energy, which means that you cannot apply this for the situations where you have unknown kinds of forces or you have friction forces. So let me write that. Above can be used only if forces acting on the system are such that the work done by those forces can be written as change in potential energy. Okay, so I should also write that friction or unknown kinds of forces, unknown forces, you know, like when you are given a block and somebody says there's a force of F Newton applied on it, you don't know anything about the nature of that force. So those would be unknown forces. Friction or known forces do not have an associated potential energy function. So the forces actually for which we can write the work done as change in potential energy are also called conservative forces. So write that the gravity in this case and linear elastic forces are conservative forces. So if in a system you draw a free body diagram and you find that the only forces acting are gravity and linear elastic forces, then you can definitely use conservation of mechanical energy principle. But if you have friction or unknown kinds of forces acting, then you cannot use this principle, conservation of mechanical energy. In that case, you would have to use the general formula, which is that W is equal to delta T. You would have to compute the work done by individual forces and equate that with change in kinetic energy. So let me write this. This is always valid. Okay. On the other hand, delta of T plus U equal to 0, which is the mechanical energy conservation principle, valid only if forces are conservative.